So parametric modeling, right? The title of this presentation. Parametric modeling attempts to define a mathematical expression that approximates the behavior of some observed or ideal data set. For example, we could try to fit a line to model inflation data over the last 5 years, and then we could use that line to try to predict inflation over the next 2 or several years. Now, those of us that are, scientists, engineers, mathematicians, or training to become one of those, we should be pretty familiar already with that type of extrapolation. Regression describes the line fitting process or the tuning process. It's tasked with defining an optimal set of model parameters, which we refer to as theta. Consequently, after regression, we expect the mathematical model to more closely match the observed or ideal data. A linear regression is one that employs a model like y equals mx plus b. That's a type of expression we should all be familiar with. And we use a loss function to quantify how accurate or inaccurate a parametric model is. Now, one simple type of loss function would simply be to quantify the difference between the ideal y values or outputs and the estimated y values or outputs. Fortunately, for the linear regression, this specific type of linear regression we're discussing here, which employs a mean squared error loss function, we'll talk more about that later, does present a closed form solution. We are going to come back to this, so I'm not going to dive into the details of this expression right now. However, x represents the inputs and y represents the ideal outputs. Other regressions, with one example being logistic regression, that's the topic of the next module. Now, they do not necessarily present a closed form solution, and as such, they may require iterative or nonlinear types of solution methods.